Hello, we are starting topic 3, gates and timing. Okay, it's really not only gates and timing. It's transistors, simulation, and gate level simulation, transistor level simulation, and timing involved in the gates and the delay of the gates, the delay of the transistors. So we are covering large concepts here, okay, which is very important in understanding what is coming next. I'll talk about simulation model. Okay, why simulation? We will talk about that in a few minutes. Then I talk about transistors. Then I talk about upper level building blocks, and which become gates. And then we say, well, some gates are a little bit more complex than other gates. We call them complex structures. And then we do some examples. So let's start with simulation model. See, eventually in this course, we will be talking about circuits with millions and millions of transistors. Okay, the circuit I'm showing here is really not a million transistors, but there are a good number of transistors here. And I have to be able to analyze this. In order to be able to analyze this, I have to show the circuit diagram, something like what you see up there. Actually, that circuit diagram corresponds to that layout that you are seeing there. Notice the NMOS and PMOS transistors, those little transistors that we'll be seeing larger views of them in a few minutes. There are transistors like this, and notice that there are not too many transistors here. But then in order to be able to analyze this, I have to be able to put the transistor circuit and then say, well, what happens if I have a certain value here? Let's say we have already decided that our values are only 0 and 1. Okay, if I have a 0 here, this is what's going to happen. If it's a 1, this is what's going to happen, and analyze it, and this and this. I have to do this. Okay. Even for a small circuit like this, you won't be able to go through all the events that are happening, especially if you consider the timing of the transistor, which in a few minutes, I'm going to talk about the timing of the transistor. I'm going to tell you that transistors on, off is not going to happen immediately. There is a timing, there is a delay. Considering all these delays, evaluating a circuit like this is not easy. Okay, so what do we have to do? Well, we have to model this circuit, which means that I have to describe it in a way that the computer program understands it, as if it was a real circuit. And then I give this model to a program that is called a simulation program. If it were a real circuit, I wouldn't give it to a simulation program. I would put it on my test bench and I would test my actual circuit. Therefore, simulation is referred to as testing the model and not the actual hardware. Okay, so I'm doing testing, but not testing of the actual circuit. I'm testing the model. That's why I call it simulation. But when I'm doing simulation, I have to simulate this computer program that is a simulator. It has to simulate it according to the way the circuit behaves. Okay? What is important for me? Is 1 femtosecond timing important for me? Maybe not. 1 picosecond? Maybe not. Okay? Do I wait for perhaps the operation of, let's say, a multiplication to complete, and then the timing or the delay of that is important? Well, it is important, but there are a lot of other details that this ignores. And therefore, simulation has to be according to the information that I'm extracting, that I am trying to look at. And therefore, a model for the simulation program has to be based on the information that I like to get out of that simulation. Okay? We are talking about modeling. To be honest with you, the 0 and 1 that we have already talked about are not real. Those are also models. Those are models for a transistor being on or off. For a high voltage or a low voltage, those are models. So everything we are doing in this course is model. And we have to understand that. And that model is simulating. Simulation is testing the model. We said this already. Many transistors to analyze, so I really need someone to simulate that for me. A computer program to simulate it for me. I have to simplify my analysis so that in a given time, I won't have to run days and days of simulation in order to get some result out of it. Okay, and therefore we have to have transistor models that are simplified. I have to have appropriate simulation technique for the information that I'm trying to get out of that simulation. All right. Simulators or simulation programs are different types. One is event-based simulation. I will get to that in a few seconds. One is cycle-based simulation. Cycle-based simulation means that a certain cycle, which later on we will see in this course, the clock cycle. In each cycle, assume that all the propagation, all the delays of the circuit have been reached a certain steady state, and then go to the next stage, the next clock. That's called cycle-based simulation. Another simulation method is oblivious simulation. Oblivious simulation means regardless of what circuit you have, go based on a certain time interval. Okay, so we are doing time interval simulation. Okay, time interval. And with this time interval, simulate the entire circuit. So if you go back to the circuit that I was just showing a few minutes ago, it means that in each time interval, maybe 1 picosecond, maybe 1 femtosecond. Okay, let's say 1 picosecond. In every 1 picosecond, simulate the entire circuit, then again, then again, then again. Then eventually you will have a list of values for every 1 picosecond simulation. This is a good simulation, except that it's too slow. But then, somewhere between cycle-based and oblivious simulation is event-based simulation. Event-based simulation says this. It says you don't really have to simulate every 1 picosecond. What you do is you wait for something to happen in the circuit. If that something changes some other input of some other part of the circuit, just put that part in your activity list and then only go based on this, only simulate the circuit that under inputs an event occurs. Therefore, we call it event-based simulation. Okay, so maybe for several milliseconds, nothing is happening in the circuit, or maybe at certain times, only a little portion of the circuit has events in it. So why do I have to simulate the entire circuit, the entire 10,000 transistors of the circuit, only because one portion of the circuit has events on it? I'm not going to do that. What I will do is I will go event-based simulation. And when an event occurs, I will put all the gates that have seen that event on their inputs, I will put those in my event queue. And then we'll get those event queue one after the other. The simulation we will be doing in this course is event-based simulation. And the simulation model for the elements of the circuits that we do is event-based simulation model. Okay? So if I write the transistor, I don't write the transistor as if it's going to be simulating in the SPICE program. That's electronic program for simulation program for detailed electronic circuits. Okay, I'm not writing my model for a SPICE simulation. I'm writing my model for a very coarse, okay, more abstract event-based simulation. And the reason I do this is because I want to have millions of transistors to simulate without having to wait days and days in front of the computer for it to finish simulation. Simulation evaluation only occurs when an input of a component, a gate or a component or a transistor or whatever changes. Okay, so if this is my transistor, something happens here, I say, oh, okay, I have to simulate this. If nothing happens there, I say, well, nothing has changed, so the transistor keeps its value. Okay? We have something like this. This is called a timing wheel that includes the event queue. Okay? Something happens. Let's say, for example, B changes at 1. See? B changes at 1, so that's put in the event queue. D changes at 5, time 5, so that's put in the event queue. Okay, and then the B changing at 1 causes something to change on C at 2 time units later. I'm saying delay is equal to 2 time units later. And therefore, at time 3, C changes. C comes into this event queue, but then D still in the event queue. At time 3, what happens is this gate has some change on it. And then this gate also has a change on it at time D, and therefore I will evaluate this. So what I'm really saying, of these two gates, I'm not going to simulate both gates all the time. If event occurs on this gate, on the gate on the left hand side, or a component, whether it's a gate, a transistor, a large component, a whole microcomputer. If there is an event on one of the inputs, I say, well, when is this event is going to happen? When it happens, when is it going to change the output? When it changes the output, what other gates or components are going to see this change? Or what other gates and components are being affected? And I only simulate those. This is called event-based simulation. And at the end, you see this, you see exactly what I'm showing here, which is this gate. At time 4, the output of it goes to 0. At time 6, the output of it goes back to 1. This is exactly what you would be getting if you say, well, let me simulate this every 0.1 time units. But then for that, you will be doing many simulation runs. Whereas for this, what I'm getting, I'm doing very few simulations, and those very few simulations are only incorporating a small number of components and not the entire circuit. All right, so we said simulation, so we decided it's event-based, and then we decided that we need a simulation model. Okay, this is the simulation technique. We need a model for our transistors, for our gates, and things like that. All right, our components. We have decided that everything is binary, so let's say our components are binary. Okay, our components only change 0 and 1. But then there are other situations that may happen. What if one of my components is driving a line with a 1, and another component, a different component, is driving the same line with a 0? What do I get? Do I get a 1 or do I get a 0? Remember, I said 0 and 1 are models, are not actual values. And if I drive a line with a 0 and a 1, something else is going to happen. It's not going to be 0. It's not going to be 1. It's going to be something bad. Because I'm driving a certain line with supply voltage coming from the supply and also connecting it to ground, which is 0. How do I represent this? Do I scream something bad is happened? Or I can do this. I can say, well, things that are not all that perfect, let's call them the X value. Okay? And the X value is the value that is representing an unknown, an uninitialized, a bad value, a conflict, and things like this. So, what I have is 0 representing low voltage, a 1 representing high voltage. High voltage means driven by supply. Low voltage driven by ground. An X for a line that is driven both by supply and ground. What if there is a line not driven at all? It's not connected to ground. It's not connected to supply. It's not a 0. It's not a 1. It's not an X either. How do I represent that value? Well, that's another value which I haven't discussed. Different from 0, 1, and X. That's the fourth value. I call that a Z value, a float value, no value. Okay? High impedance value. And therefore, all my simulations and all my simulation models are following the 4-value logic system. 4-value logic system. Not a 2-value logic system, not a 0 and 1, 0, 1, Z, and X. And then the simulator that is using this 4-value, using these components that I have, or these models that I have, will also be displaying 0, 1, Z, and X, which we will see actually. We will see a simulation run that shows a Z, an X, a 0, and a 1. All right, that's it for the simulation. Okay? So when I draw this, this is a transistor. That is close to the way a transistor is built. Obviously, this is not a transistor. The diagram you see in front of you, that's also a model. But this model is not for simulation. This model is for you and I to communicate and understand how a transistor works. Okay? Or maybe this is a model, this is a painting. I like to put it on my wall, but still is a model. What purpose does it serve? Well, it serves the purpose of decorating my room. But it's not a simulatable model. I'm going to take this, analyze it, and then come up with some simulatable model that resembles or mimics the actual physical transistor. A transistor has a source or a drain, a source, it doesn't matter. You can call either one whatever you want. I mean, you can call the one on the left a drain, the one on the right a source. And then it has a gate. The gate controls the connection between the drain and the source. You also have substrate. This is an NMOS transistor. For an NMOS transistor, there are minority electrons, charges inside the substrate. They're just there. They're just relaxing. Okay? They're providing a very, very high resistance between these two we call them diffusion areas, which are conducting. The transistor has the drain, which is a conducting material, which is diffusion, that means heavy dope of electrons. A source, which is heavy dope of electrons. So when you have the silicon with a lot of electrons on them, it means that it is conducting. There is also the gate, which is polysilicon, which is also conducting. And then between the gate and the substrate is silicon dioxide, which is not conducting. Okay, which is not conducting. So I have drain is conducting, source is conducting, gate is conducting. The silicon itself is not conducting, but it does have few electrons in it. Okay? If I put a positive voltage between the polysilicon and the substrate, what happens? That positive voltage will attract the electrons that are in the substrate towards the silicon dioxide, towards what we refer to the gate of the transistor. Okay? So this is what's going to happen. When the electrons that were minority charges in the substrate come up there, and then the the drain and the source were also conducting material. Now I have a conduction path between the drain and the source of the transistor. What it means is by putting a positive voltage between the gate of the transistor, this is the gate, between the gate of the transistor and the substrate of the transistor, now I've been able to make this a switch, and therefore the source and drain connect. This transistor looks like this. This is the gate. This is the, I think we call this one drain. This is the source. When there is a positive voltage on the gate, the transistor conducts. What it means is, when I have a 1 here, the transistor conducts both ways. When I have a 0 here, the transistor does not conduct. Okay? What I just said is, again, I am modeling. I'm showing you, I'm talking about the model of the transistor. This is the model. Okay? I have another type of transistor. This is called an NMOS transistor. I have another type of transistor which is called a PMOS transistor. Both of them have channels. Both of them, when conduct, the channel will be conducting. Both of them, when they are not conducting, they have, in this case here, NMOS transistor, there are very few electrons between the source and the drain. And therefore, when it's not conducting, it's not exactly not conducting. It has a very large resistance between the gate, or we call it open gate. There is another type of transistor which we refer to as the PMOS transistor. Things there are completely the opposite. It has poly, still it has silicon dioxide, and then the source and the drain of the transistor are non-existence of electrons. That means they are holes. If electron has a negative charge like this, there are little electrons in the substrate. In a well, of a PMOS transistors, there are few holes, that means positive charges. And when you put a positive charge on the poly, a positive voltage on the gate, you will push the positive charges in the well or in the substrate away from the gate, and therefore it's not conducting. When you put a negative voltage, let's say something like this, when you put a negative voltage on the gate, the negative voltage will be attracting the positive charges, and therefore there will be a conduction path between the two diffusion areas, which are doped with positive charges. Okay, positive charge means hole, means not non-existence of electrons. Negative charge means electrons. This is a symbol for PMOS. We will be using the simplified notation. This is a symbol for NMOS. NMOS meaning N-channel, negative channel transistor, metal oxide semiconductor. This one is PMOS, that means positive channel MOS transistor. Okay, that means the channel is the channel on the left hand side is P, the channel on the right hand side is N. A channel has a length and a width. This is the width of the channel. This is the length of the channel. Okay? The further away the two diffusion areas are, these are diffusion. The further away they are, the longer the length is, and therefore the larger the resistance of the channel is, or the on resistance is. The wider the transistor is, the area that the two diffusions face each other will be a larger area, and therefore there is a smaller resistance, on resistance. Not only that, look at this. Here I have a conducting material, and then there is another conducting material here. Okay? Between these two conducting materials, what do I have? I have silicon dioxide, an insulator, no conducting. What do I have then? Well, conducting, no conducting. What I have is, I see a capacitor. Okay? Not only that, I see a capacitor here. Not only that, I also see a capacitor a little bit over here, because see, the N on the left-hand side is conducting, and then the poly is also conducting. So there is a little bit of area that there is a capacitance here as well. Also, there is a capacitance here as well. Okay? Not only that, well, look at the two N areas. These are conducting, and then there is a non-conducting material between them. What it means is there is also capacitance between the source and drain. But the only significant capacitance, which you also see in the symbol of a transistor, is the gate capacitance, the capacitance between the poly and the substrate. And that capacitance is exactly this capacitance. Oops, sorry. Is exactly, see, this capacitance is exactly what I'm showing over here. Or what is shown over here. Okay? That's called gate capacitance. Now tell me this. I have this transistor. Let me clean this up. This is the length. This is the width. The size of the capacitance is related to L times W. The area that silicon dioxide is separating the conducting material on top and conducting material at the bottom. And therefore, the capacitance is L times W, is proportional to L times W. How about the resistance? The resistance gets smaller if L is smaller. It gets larger when L over W. Okay? When W becomes smaller, R becomes larger. Okay, when W becomes larger, it means that the area that these two conducting materials, the P's or the N's, are facing each other is a large area and therefore less resistance. Both for the PMOS transistor or for the NMOS transistor, the resistances and the capacitances are the same. This follow the same rules. But then, for the NMOS transistor, the electrons are the ones that are creating that resistance. The mobility of electrons is higher than the mobility of holes. What it means is for the same size transistor, the one on the right, I'm going to erase this, the one on the right and the one on the left. For the same size transistor, the resistance for the p-type is formed by, or is actually formed by traveling of the holes. The resistance for NMOS is by traveling of the electrons. Okay? Going from here to here, from here to here. Same thing here, here to here. And since mobility of holes is smaller than mobility of electrons, this for the same size transistor, a p-type transistor has a channel resistance, R channel. Let me do it, R channel. For the NMOS, R channel. For the PMOS, for the same size transistor, resistance of the PMOS is larger than the resistance or the channel resistance of NMOS. Okay? And that's what we are saying here. This is the gate capacitance, this is the gate resistance, and we are ignoring all other resistances or capacitances. What is this ignoring? Actually, I'm talking about the model. Now what I'm saying is an NMOS is a transistor with some capacitance here, Cg, some on resistance, channel resistance, on resistance. That means if it's connected, it has this resistance here. Okay, I'm ignoring the off resistance. Remember when I was showing this, I said, well, even if it's not conducting, there is still electrons between the two N-type materials. So there is still some resistance, but it's so large that I'm ignoring it. When I'm ignoring it, means that I have a model that does not include the off resistance. It only includes the on resistance. And then I have the gate capacitance. And the gate capacitance here is the capacitance that I'm considering. There are, like I said, other capacitances as well. But then my model does not include those capacitances. My model only has a gate capacitance and an on-channel resistance. That's it. So when I talk about the model, this is what I mean. I could make it more complex. I could make it far more complex. But I'm saying for logic circuits, this is good enough. This is actually way too much. In the same lecture, I will go up and say, well, true that this is fine. This is a good model. But then I cannot afford running R and C simulations all through my circuit. And therefore, I have to simplify what I just said. How do I simplify it? I use Verilog simulation program. Verilog is a hardware description language. Verilog has notations for all hardware components. Hardware components can be described or can be modeled at various levels of abstractions in Verilog. Verilog can go as far down as transistor, not transistor like analog transistor, a transistor switch, as far down as transistor, and as far up as a complete processor, or a complete system, or a complete, let's say, vehicle detection system. It can go as far up as that and as far down as transistor. But for the transistor, it follows switch model. And switch model is not exactly RC model. It's not this. Switch model is the model I'm describing here. Transistor can be described as easy as this one here. An NMOS with a drain, remember the drain, one of the N-type materials. A source, the other N-type material, and a gate, which is the poly, which is the one that controls the connection between the source and drain. That's it. So if I want to describe my circuit in terms of transistor, this is all I need. And I have two transistors connecting to each other. I can just say, well, this is transistor 1, T1. This is transistor 2, T2. Okay. And then this is G1, this is G2, this is, let's say, A input, this is W output, this is Y output. How do I represent this? I do it this way, NMOS. Okay, I have the choice of putting a instance name, which is T1, the one on the left, and the output of it is W, the input of it is A, and the control of it is G1, or the wire connected to G1. The other transistor I have is T2, and T2, the output of it is Y, the input of it is W, and G2 is the control of it. That's all there is to it. See, here I said this is representing my transistor. I just build a circuit with two transistors, and then this is how I describe these two transistors. You just wrote your first Verilog description of this little circuit that I have over here. Verilog tells you, well, if you don't want to put the delays, don't. Okay? Still works as a switch level, still works as on-off, but then no delays. Nothing here in what I've shown you so far. Okay, nothing here is representing the resistance here and the capacitance here, but we all know that resistance times capacitance gives you a delay. This model doesn't have a delay. But then Verilog says, well, if you have to have delays, I'm not going to give you R and C values, but I'm going to give you these three delay values. A to 1 value, a to 0 value, a to Z value. Okay, to one value, meaning that the delay after which the output, okay, the output becomes 1. In this case, my output is W. In this case, my output is Y. And the output is the one that I write first. It says, when something happens and the output is changing to 1, that change occurs after the delay that you have put over here. That's why we call it to 1 delay. This is, if something happens and the output changes to 0, this happens after to 0 delay. If something happens and the output changes to Z, it happens after this. Let me show you all 3 cases here. And I'm showing it for NMOS, PMOS, basically the same thing. Here's an NMOS. This is 1, that means it's conducting. This is 0, and because this is conducting, this is also 0. Something happens. This 0 changes to 1. This 0 changes to 1. Because of this change, this 0 also changes to 1, but then with a delay from the time that the input changed to 0. The delay here is called, changed to 1. The delay here is called to 1 delay. The delay here is called to 1 delay. Next, same transistor. This is 1, this is 1, and therefore this is 1. At one point, the input changes to 0. It takes some delay, and this one changes to 0. This is the to 0 delay. And this to 0 delay is the second timing parameter in description of the transistor if you decide that you want to represent the delays. Okay? I have a third case. My transistor is conducting. Maybe there is a 1 here, maybe there is a 1 here, and it is conducting, therefore this is a 1. My transistor source changes. No, my transistor source doesn't change. My transistor gate changes to 0. That means my transistor is no longer conducting. After a delay, my output 1, which is this, my output 1 changes to Z. Changes to Z. This delay is to Z delay. Okay? How about X? What happens if I have 2 transistors? One is driving 1, one is driving 0, and then at one point the output becomes X. What's the X delay? Well, it's the larger of the 3. What if I drop one of these? Is the one that is dropped is the larger of the 3. What if I only put 1 in there? Well, all 3 delays is that 1. Therefore, I can say NMOS, and therefore here I can put here sharp sign 3. It means that all the delays are 3 nanoseconds. Sharp sign 5. All the delays are 5 nanoseconds. Okay? And that's a transistor model. This is an event-based transistor. Let me say it better. Let me say it correctly. This is a transistor model for event-based simulation. What it means is this simulation will only do something if there is an event here or here or here or here or here. T1 and T2 sit quiet, do absolutely nothing if there is no event on their inputs. They just sit there. They just look. And if some noise comes in and changes W, since this is the input of T2, T2 will see that and will react to it. And react to it after the delay is specified, which is, in this case, what I'm showing is 5 nanoseconds. What I'm showing here is T fall or to, actually, here. I hate to erase my art. Okay, this is to 1. This is to 0. Okay, and this third one is to Z, or turn off delay. This is good for now. We will continue with, now that we know the transistor, we know the delay, we know the model, we know the simulation. Next thing is, let's do an inverter. Let's use this transistor for something useful. And that useful is an inverter. That comes next.